What's up with Bono? Hello?
Hello.
Hey, Jeremy. Hey, Matt.
Howdy.
Yeah. Okay. I'll set this up. Just wait for Bowden. What's happening? Oh, here, Bowden is just logging in. Okay. Yeah, today there was this during the last class, you guys pointed out that things were not matching up in the homework. And to a certain extent, that is correct, actually. I went ahead and I was telling that 45 minutes down the line in the recording, I was seeing that, oh, something is there. So I think it is good to bring that up. But it's a very minor thing. Most of it was, but it's good to point out. So let me say homework 5 is due on March 12th now, on Friday. But let me keep the last problem optional. Anyway, I'll be doing most of it here in class, but I'll encourage you guys to work on it, but I don't want to grade it on it, so that I think it is fair that way. Midterm 2 is on March 26th. Friday. Again, I won't ask the detailed version of it, but since we spent a good amount of time now making series expansions in K-square, so we should we can expect that there will be some problems related to how to expand things in a series. Okay. Okay, so what was the point? Let me clarify so I can summarize things. So we have a circular wire, and just for a diagram and parameters that goes with it. So that's your current I in this, and there is a radius of the loop A here, and that's your position vector R. Right? So, and if I were to draw a diagram separately here, that's your vector R, that's your Z, that's your rho and A that is no conditions, and if we have an exact expression, this is everything is known about it. So let's say the vector potential due to this current carrying wire, we said was it will be in the direction, tangential direction of the loop itself, and it is mu naught over 4 pi, and it was given in terms of what was this 4ai over z square plus rho plus a the whole square. And this is an exact expression I'm writing. I'll write the approximate expression quickly. Minus of the still visible as k. And these are elliptic integrals, recall. And we showed that let me not do that here. Yeah, basically we try to approximate this term in square bracket. The magnetic field similarly, in exact everywhere, no approximation at all, whether you're close to the axis, away from the axis, close to the wire, away from the wire, no issues at all. And that's given in terms of there is a component in the z hat direction, and that is what 2i. So this is 2 times I z square plus rho plus a the whole square. Okay. And minus we had z square plus rho square minus a square. That's the combination we were struggling, or I was struggling with last time. Minus a times e. That's a component in the z direction, but we know that the magnetic field of this loop has this feature, and then that's your magnetic field. So somewhere around here, if you're close to the axis, there is slight bend, so there is a rho component and z reduces, right? So it's plus, but I write it as a negative, so the exact expression shows up as a negative rho hat, but whatever is in here is actually positive. So it's 2i over z square plus, and there was this z over rho, and pretty much the same as this. That is a sign change there, rho square plus a square, and we have z square plus. Okay. That's all good. This is the complete expression, but we were interested in what about things close to the axis. In fact, I was saying k square very much less than 1. This is typically applicable for close to the axis. But as I'll show that, to capture everything, we have to be careful with how many terms we keep. Do we go to k square or k raised to 4, and so on. In this limit, these things, these expressions get much simpler. There is no more elliptic integrals we are worried about, and we have the expression to be. We can write it as in terms of what is this magnetic magnetic moment of this loop, and we have a rho, right? That's I'm looking at the notes here. So this is z squared. This is what we want to show, but this we showed in the class, right? So this was keeping up to order k squared, and we used the fact that the square bracket in the expression for a was equal to 3 by I think it was pi by 16, sorry. So it is pi by 16 k squared. We kept to reasonable orders, and we showed that this is what shows up. And the magnetic field similarly simplifies to be z hat mu naught over 4 pi times I times pi a square over same idea 3 by 2, but now there is a small change, and the change is if we were on the axis, if rho was equal to 0, that's the factor 2, right? I mean, if you set rho equal to 0 everywhere, that answer is exactly true. You can do it using elementary ways, but now you reduce this by a certain amount, so that's rho times rho plus a divided by z squared plus rho plus a. That's a correction in the z component, and similarly there is a small correction in the rho hat component also, right? In the radial direction. Like this is sort of the result, if you want. Square plus rho plus a the whole square 5 by 2, and here we said this was 3 times rho times z. That was what we had. And how did we proceed to do this? There are two ways of doing this, right? One is you start from the expression for a and use the series expansion, and you get here, you drop all the k raised to 4 terms, and you get this. Do the same thing for the magnetic field. You can start from here, drop all the k raised to 4, and you can get this. But there is a check also in here that if you were to start from the approximate value of a, do the cross product. So that is b is equal to del cross a. And that's what we had done in the class. We started from here and got this. And now the idea is that can you get directly from here, and we should get the same expression. And let's do that, and we will indeed be able to do a lot of it, except that there is one term we won't get, but that is because there is an approximation, additional approximation that goes in. Okay, so let's go with what we did last time. So that's the first step, and that's now can be seen very easily. I can put that. This is a square over z square plus rho minus a the whole square. That was what we did. And how do you proceed with this? So you would say, I want to write this as close to possible as a k. Remember my definition for k, I should put that here, k square. Yeah, k square is 4 a rho over z square plus rho plus a the whole square. It's pretty much manipulation here. We want to write this expression as much as possible in terms of k square. So I say this is rho plus a the whole square so that I can get this denominator part somehow there. But I have changed this, so I have to subtract 2a rho. Divide, do the same thing in the denominator. I want to write it as rho plus a the whole square. But if I want to write that, there's already a minus 2a rho. I am adding a plus 2a rho, so that's a minus 4a rho. Divide this out on both sides. So I have 1 minus 2a rho divided by z square plus rho plus a the whole square. That's the numerator. And in the denominator, I have 1 minus 4a rho over z square plus rho plus a the whole square. Right, this is what we did last time. It was not very transparent at that time. But now what I can do is I can divide by 2 and multiply by 2. That way I get a 4a rho, that's a k square there. So what this is equal to is that this is 1 minus k square over 2 divided by 1 minus k square. And let me keep it like that. So that's equal to 1 minus k square over 2 divided by 1 minus k square. Series expand 1 over 1 minus k square. If you series expand that, this is equal to 1 plus k square plus k raised to 4 plus order 6. Order k raised to 6. And that's because 1 over 1 minus x, when you take it to the numerator, all the factorials exactly cancel the ones from the power, and that's exactly this. So what I can say is that this is 1 minus k square over 2, and you multiply by 1 plus k square plus k raised to 4 plus order k raised to 6. And we showed that this is exactly equal to, if I were to take care of all the multiplication, let me not repeat that here since we did that last time. I can write that right away here. So that's 1 plus k square over 2 plus k square k raised to 4 over 2 plus order k raised to 6. That was what we did last time. Let me write that down here so that I get some space. And so this whole expression is equal to 1 plus k square over 2 plus k square k raised to 4 over 2 plus order k raised to 6. That's what we want to use. Let's now work the same thing. Same thing with the other expression. We have z square plus rho square minus a square over z square plus rho minus a the whole square. It's slightly trickier, but the idea is the same. We want to keep as much as possible in terms of k square. So if I want to write this as k square, what will I do? So I'll do z square. I already know the expression here. So I will do z square plus rho square plus a square divided by minus 2a square divided by z square plus rho minus a the whole square. But change the denominator here. Change the denominator there to whatever we did earlier. So that's z square plus rho plus a the whole square minus 4a rho. So the numerator I subtract a minus 2a squared, and the denominator I write it as minus 4a rho. This one I already know what it is. This is equal to 1 minus, if you want, this is simply 1 minus k squared over 2 in the exact form. And here, we want to be careful. Now I want a 4a rho, right? Only then I can identify it as a k square. So I multiply by 2 times rho and then divide by 2 times rho. So that's 4a rho. So if I collect the a over 2 rho outside, then whatever is remaining is k square in the numerator, because I collect this 4a row with z square plus 4a square, and in the denominator I'll simply have 1 minus k square. That's your expression of z square plus rho square minus a square in terms of k square. Notice that there is a little part that remains, and as I said, as much as possible, we write it in terms of k square. As a series, if you were to do this, you know the series for this, that's already 1 plus k square over 2 plus k raised to 4 over 2 plus order k raised to 6. And the second piece is minus a over 2 rho. And I will again expand this out. And what is the expansion? Let's look at that. I'll do that here. So k square over 1 minus k square is k square times series expansion we said is 1 plus, 1 plus k square or plus k raised to 4 plus order k raised to 6. That's the same as I start from k square, that's equal to k square plus k raised to 4 plus k raised to 6, but already I'm neglecting k raised to 6, so I can drop this, right? So plus order k raised to 6. Okay, so we have this term here, so that's k square plus k raised to 4 plus order k raised to 6. That's our expansion if you want how many orders you want to keep in there. And at this point, we just have to put it back in our expression for magnetic field, which was down here. For you guys, it is a little behind. So what we want to do is have the series expansion here. Now we have the series expansion for these quantities. Put it all in this, and let's try to recognize what our magnetic field will be in that small angle approximation. Is that clear, the strategy at least, what's going on? Okay, so if I go with that, so maybe I can do a little bit more here. Yeah, so earlier we said we called we defined C1 to be equal to, so C1 to be k minus z square plus rho square minus a square divided by z square plus rho minus a the whole square times E of k. Let me call this C2 first. So let's call it C2. C2 is with the plus sign here, and the rest everything is exactly the same. So C1 would be actually because there is the term that contributes to C2 already in there. So C1 actually is equal to C2 because this term is exactly that contributes to C2 minus, when I substitute that there, that's plus A over 2 rho times k square times 1 minus k square times E of k. Because this is a minus sign in there, substitute it in there, it gives you a plus sign. So the magnetic field is given in terms of C1 and C2. If I were to write that down in there in your notes. So this will be C1 and that's your C2. Okay, we already worked on C2 last time, and I can quickly sketch what that is. So C2 would be equal to k minus 1 minus k square over 2 over 1 minus k square times e of k. That's what it is. And that's equal to, put that all in a series. This is pi by 2, 1 plus k square over 4 plus 9 over 64 k raised to 4 plus order k raised to 6. And we just now found the expansion for this quantity, that was 1 plus k square over 2 plus k square k raised to 4 over 2 plus order k raised to 6. And finally, the expansion for e, which is 1 minus k square over 4 minus 9 over 64 k raised to 4 plus order k raised to 6. And hopefully it's all in the board space. Okay. We expanded this part we already did in the last class, and we noticed that there's a lot of nice cancellations. The leading orders all go away, and this gives you exactly, if I remember right, I think I have it here. Yeah. So that's exactly equal to minus 3 pi over 32 k raised to 4 plus order k raised to 6. And that should be, is that okay if I skip that, just so that we have more time? We exactly did that last time. So C1 will be equal to, since C2 we already know, so that's minus 3 pi over 32 k raised to 4 plus a over 2 rho times k square over 1 minus k square, we said is k square plus k raised to 4 plus order k raised to 6, and then we have pi by 2 times 1 minus k square over 4 minus 9 over 64 k raised to 4 plus order k raised to 6. Okay, that's equal to
minus 3.
oh, minus 3, yeah. Oh, that also I wrote it wrong, right? Yeah, this should be minus 3. Thank you, thank you. Minus 3, yeah, otherwise I'll get stuck. Okay, thanks for keeping an eye. Yeah, I think, yeah, that's what it is. And k square, yes. So that's equal to plus a over 2 rho plus a over 2 rho, and let me put the pi also, right? So that is pi a. Let me collect this together. So it's pi times a over 4 times rho. Right? Yeah, let's write it like that. Yeah, over rho. And this is will be equal to, now let's multiply this out together. This is k square minus k raised to 4 over 4, like this multiplied by 1, this multiplied by this. The next one is 4 plus to 6, right? That's order k raised to 6, I don't keep it. Then next comes k raised to 4, I multiply k raised to 4 here, k raised to 4 times 1. Then k raised to 4 multiplies k raised to 2, that's order k raised to 6. So many of them do not contribute. Right? Only 3 terms in this are less than order k raised to 6. So in that sense, it is significantly easier. And now we have this to be, let's put this together. So this is minus 3 pi over 32 times k raised to 4. Then we have plus pi a over 4 rho times k square, and this is 3 by 4 k raised to 4, right? So this is 3 by 4 k raised to 4. So that's the same as plus pi a over 4 rho times 3 by 4 k raised to 4 plus order k raised to 6. Is that clear what I did? As of now, I have just collected these terms. The only thing I did was that I combined these two equations, including the sign. Let's replace them with our radius so that, oh, was I visible there? Barely. Okay, hopefully you guys managed. Okay, so the only thing I did was I collected these two together into 3 by 4 k squared. That's only. Okay, so that's equal to minus 3 pi over 32 k raised to 4 is 4 a rho square divided by z square plus rho plus a the whole square, and this is squared now. So that's just the definition of k square being put in.
You don't want to combine your k raised to 4 times.
Because there is an a over rho extra, right? I cannot exactly combine them, right? So I'm stuck with whatever I have there. But you will notice, yeah, in the next step we will be able to combine, but they will come as two different pieces. Yeah. So yeah, this looks same, but there is we cannot combine, right? Yeah, but it probably can be combined as a plus rho. That's okay. If you want, you can combine it. That's just way of yeah, good. And this one is plus. Maybe I should write this before because this is a leading term, right? So maybe I should do that so that structure comes out nicely. So let me do this first. Pi a over 4 rho times k square is 4a rho over z square plus rho plus a the whole square, right? That's this term. That's this term taken care of. Next, let me write this, and then I'll write that. So this is minus 3 pi by 32 k raised to 4. So that's 4a rho whole square divided by z square plus rho plus a the whole square. And finally, there's a plus pi a over 4 rho times 3 by 4 times 4a rho the whole square divided by z square plus rho plus a the whole square. Okay, should be all fine. Okay, put this all as much cancellations as we can do. There is a row that cancels out. So then there is 4 also goes away, and we have pi a square, which we have been trying to keep it with to identify the magnetic moment of this wire, divided by z square plus rho plus a whole square. So there's only one power here. So that's power 1. And there was a 2. That's yeah. Okay. And if I were to take this common out, let's see what are the cancellations that happen here. There's a 4 times 4, that's 16. So I can cancel that. 4, that's a square. 4 times 4 is 16, and that is a 2 in here. That's one thing that happens. Same thing here. There's 2 4s that cancels out, and there's also one row that cancels out. So what I can keep this common anyway outside. So the correction will be 1 minus 3 by 2 pi a square I've taken out. So pi a square has gone out. So 1 minus 3 by 2 is staying outside. And what is remaining there is rho square. And of course the denominator, which is z square plus rho plus a the whole square. And power 1 now, because already I have pulled out 1 power. That's rho square. What is the rest of it in here? So pi is gone, a is gone, a square. So one of them, there is 3 a's in it, right? That a and an a square, there are 3 a's in it. So there is an a that will remain. Right? And rho square, there is a rho that remains. That's the 2 quantities that remains. And 3 by 2 is common for both. And this comes with a negative sign. And that's your C1 if you want. If you put this all together and look for what the magnetic field is, so we basically have that expression for the magnetic field. Now put this inside our expression for magnetic field earlier. We have z hat times mu naught over 4 pi. Let me pull this out. That is I times pi a square. There's a factor of 2 out there, and there I will bring that in so that I can write it here. And this one combines with the square root expression there and gives me a 3 by 2. And the factor of 2, I pull that in, just why? Because on the axis there is a well-defined expression for b, and that becomes with that factor of 2. That's 2 minus 3 rho square minus a rho divided by z square plus rho plus a the whole square. That's a z component. What is this? In it. Okay, better. And I think I have space for writing the rho hat component also there, so it's plus rho hat. And it is a, oh, we did yeah, C1 will be exactly here, right? 3 pi by 32. Yeah, so let's do the C2, process that a little bit in the top. I think we did this last time. Yeah, we did this last time, but let me do that here again. So this is equal to minus 3 pi by 32 times k raised to 4. So that's 4a rho the whole square divided by z square plus rho plus a the whole square and square. Do the same cancellation, 4 cancels out. This gives you a 2 and pi a square and rho square, right? So this is, yeah, so this is minus of pi a square divided by z square plus rho plus a the whole square, writing it in the same form as what we have here. And there is a 3 by 2 remaining, correct? 3 by 2 and rho square that remains. That's the piece that remains. And if you were to put this together with what we have for the magnetic field in the second piece there, oh, I will go down in the board. Okay. So use this in here. The minus sign actually cancels. Then there is a 2 that goes away. This is pi a square over z square plus rho plus a the whole square. And I have 3 times z, so this is 5 by 2 now. And one of the row cancels out, and we have 3 times z times rho. All this is perfectly fine, and it seems like at this point, if you were to try to compare with what's the expression I wrote down for the magnetic field earlier, if I were to show that in here, right? So that is a magnetic field expression we wrote down in here. Notice there is a particular sign difference in here, right? That's a catch in there. And if you come back in for this, that is reversed in sign. If I were to take a row outside, that is reversed in sign. And of course, when you first time see this, you think that, oh, okay, in this whole algebra, we made a mistake. But I actually spent some time on this. And it seems like there is no mistake in the algebra at this stage, right? At least in the part of algebra that we did in here, there is no mistake in the algebra. But what happens is it's kind of more subtle in the sense. So let me say a few things about that. Any questions at this stage, by the way, right, as of now? Right, so we have sort of finished the calculation, except that we are not matching this tiny negative sign in there. That's all that's missing, and that could bother because it should be the same, right? You cannot, there is no room for not comparing unless there is an error, but you look at it and then you say, okay, this is actually different. So what
Internet.
I wonder how many more times this is gonna happen this semester.
I'm just ready to go back to classes normally.
As they're trying to do that next semester.
Are they doing pass-fail this semester?
I don't know anything about that stuff.
I think they'll probably decide later in the semester like they did the last two.
Just give it a couple more minutes and just peace out.
Everyone left.
Okay.
Okay, I'll record it anyway. Right, I can record it. Yeah. Okay, good. Yeah, so that's what it is. Yeah, okay. Yeah, I can combine the recording. Okay. So, yeah, I'll just start. So, what we did was that if I had mu naught over 4 pi, this becomes 4ai over v square plus rho plus a the whole square. And this was shown to be, I think it was pi over, I think I wrote it down there, right? Yeah, pi over 16 k squared. And there will be higher order terms, right? K raised to 4, something with k raised to 4 here. Right? We have to calculate that, but that can be calculated, and so on. And notice there was to get the magnetic field, we take the cross product of this. And just to give you an idea of what happens there, so first of all, k square as a rho in it. So this is k square as a 4a rho over z square plus rho plus a the whole square. Now, when you take the cross product here, there was one place where you take the derivative of a with respect to rho. That showed up. And the point here is that there is a contribution to this term even from here. This also contributes. So when we are actually dropping the k raised to 4 term, that is exactly what actually causes this sign to flip. So what's the best we can say? So in all this, okay, are we completely wrong? Do we have to redo this calculation? No, actually, we can actually save this whole calculation. What we are having is that there is a rho times rho plus a term, right? So this is one way you're getting 3 times rho plus a, and the other place you're getting 3 times rho minus a. So let's restrict our calculation to the place where this doesn't contribute. So we have to say that if I say that rho is very much greater than a, all the condition we put was with respect to r. It's the k square was with respect to r. Rho is less than r. Z is less than r. Then this is 3 times rho square, and that's perfectly fine. So what is the region in which we are talking about? So even though we said this is close to the axis, so if we want to save our calculation, so you don't want to be here, somewhere here in this regime, right? So, or yeah, in that regime is where it works, where rho is significantly larger than a. So not a very useful result, but at least the point is that you want to keep that term also. Sort of good to realize that, but I had not noticed that until you guys pointed out that it is not working out. So it is, yeah, hopefully education-wise good, but not a very good homework exercise. So you don't have to do this homework. That's, I think, fair enough to you guys. And but feel free to do it and submit it. And I'll stop here. Yeah, I realize that you guys are not there, so hopefully you'll see the recording. Okay. Thank you. And I'll stop here. And I'll combine this recording somehow with the other one.